Good evening. One concept that has not come up yet in our treatment of vectors is the idea of a basis or basis vectors. So the basis that we use most commonly in this class would be a rectangular basis, and it consists of, at least when it comes to problems in the plane, two unit vectors. So these two perpendicular or orthogonal basis vectors are each 1 unit long. And we've got one of them pointing parallel to the positive x-axis, one points parallel to the positive y-axis, and we've got some special names for these basis vectors. I'll elaborate on the word basis in a moment. Not everybody, or not every book is going to use this terminology, but I hat and j hat, those are common names for these two unit orthogonal basis vectors. So I hat, I guess it looks like a little hat on top of the letter. I think technically it's called a caret, C-A-R-E-T, but we pronounce it I hat and j hat. And, well, one reason for calling it a basis, this set of two vectors, is that any vector in the plane can be expressed in terms of these two basis vectors. I guess that sort of explains the choice of the word basis. It's like it's a basis for description of any vector. Now, if you want to describe a vector not just in the plane, but in three-dimensional space, you would need a third unit vector. And which direction do you think that would be pointing? Out of the page? IJK. No, seriously, IJK. That's the name for that set of three vectors. The third vector would be coming out of the page, and it's typically called k hat. But usually we'll just be using I and j because most of the problems we do in this class involve motion in a plane. Well, remember, vectors are scootable aroundable. So I can take this vector I hat, and if I draw it down there, it's the same vector because it's still 1 unit long and it points in the same direction as I hat. And here's a vector. Notice that this vector is one of the components of the original vector that I called A. I moved it down here, and I estimate that it's about 5 times as long as I hat. So I can actually write this red vector here as a scalar times I hat. That scalar is 5. It points in the same direction as I hat. It's 5 times as long. We've already looked at what it means to scale a vector. So this vector is the same thing as 5 times I hat. Similarly, the component in the vertical direction looks to me to be about 2.5 times as long as j hat. So I could actually express this vector as 2.5 j hat. And we already know how to add vectors graphically. If I put 5 I hat tip to tail with 2.5 j hat, the sum of those two vectors we can find by closing the triangle. Of course, that's just the original vector. So now you see, again, why we call I and j, oops, that's supposed to have a hat on it, a j hat. Why we call I and j a basis for vectors in the plane, because any vector can be written as a so-called linear combination. It's a linear combination of basis vectors. That just means you can add up I and j with coefficients in front. That's all that means. Any vector can be expressed as a sum of I and j where there may be coefficients in front of those vectors. They could be any real number, really. That's what's called a linear combination. If you're wondering why linear, well, if this was a polynomial like in algebra and this was x and y, we don't have I squared or j squared, so it's just I to the first power, so to speak. I think that's loosely why it's called a linear combination. And if we would like to be succinct, we don't actually have to write I hat and j hat. We can just put, since any vector can be expressed as some number times I hat plus some number times j hat, it's kind of unnecessary to write I hat and j hat. We can just write the coefficients in an ordered pair. Right? So this could represent the coordinates of a point, that point being the tip of the vector, or it could represent the components of the vector, however you'd like to think about it. Some books use brackets instead of parentheses. That's just a difference in notation. But one thing you should be aware of is your book likes to occasionally give these components as the polar components. Instead of stating the multiple of I hat and the multiple of j hat, they will actually say The length of the vector first, that's the magnitude of A, and then the angle that it makes with the x-axis. So obviously the way you interpret this depends on whether you're using rectangular components or polar components. Usually it's clear from the context. But right now, this first number is the component along I hat, we say, and same for the y component. If you were specifying a vector in R3 or three-dimensional space, you would have a third coordinate along k hat. And maybe the main objective in this series of slides here is to define the derivative of a vector. Because again, most of the quantities we care about in this semester are vector quantities. We talk a lot about velocity, acceleration, force, angular momentum, torque. I think I covered them all there. Many of those quantities are expressed as derivatives of other quantities, of other vectors. So we need to know what the derivative of a vector is. And it's really straightforward. You already kind of know what it is. Because think back to calculus. df dx, what is the derivative of some function f with respect to x? Well, don't forget, df is very suggestive of delta f. It's an infinitesimal change in f due to an infinitesimal change in x. Remember, f is defined as a function of x. So if x changes, typically f will change. These are two different notations. They mean the same thing. This d is still kind of attached to the f. So it's like d and f are both in the numerator because it really is a change in f over a change in x. But when you write it this way, it kind of emphasizes that the derivative is an operator that does something to your function. Like if your function is sine of x, when you take the derivative, you're operating on sine of x and turning it into another function called cosine of x. In any case, this is the relevant quantity. This is the definition of the derivative, which we will generalize to vectors. What you do is evaluate your function at some particular input, then you evaluate it at a nearby input. So if your first point at which you evaluate it is called x, scoot to the right a little bit or the left, x plus delta x, evaluate the function there. So this is really delta f, is it not? F at the other x coordinate minus f at the original x coordinate. This is change in f compared to change in x, which looks a lot like this. This is df over dx. So this is like the infinitesimal version of this. How do you get from this quantity to this quantity? You take the limit. It's the limit as delta x goes to 0. Just like what I did in that spreadsheet a couple presentations back. And you may remember from pre-calculus even that this is called the difference quotient. It's easy to remember that name because it's very descriptive. You've got a difference in the numerator and a difference in two x coordinates in the denominator, and you take the quotient of those two differences. It's an extremely literal name. Well, we're not talking about a single valued function of a single variable. That's what this is, right? When you're first introduced to calculus, you look at the calculus of single valued functions of single inputs, like, again, the cosine function. You plug one number in, it's an angle, and one number comes out. Well, now we're dealing with vector functions. And a vector has two components if you're talking about motion in the plane, or even three components. So arguably, it's like there are two quantities that come out of your function. Well, what goes in? If f here depends on x, then what does r depend on? Well, this class is called mechanics, and it's all about predicting or calculating the motion of something based on the forces applied to it, which is called dynamics. And the motion, we specify the motion in time, really. So maybe the ant is moving in time, and you can just imagine that the tip of this vector is wandering all over the place. So the vector r clearly depends on time, and that means the x coordinate and the y coordinate depend on time. So it's kind of like there's two functions of this one input, the input being t, time. So let's emphasize that by saying that the vector r is a function of time. Kind of like in the previous slide, f was a function of x. Now we're saying position is a function of time. So it's a vector function of a scalar t. You plug in the number representing the time, a particular instant in time, and you want to know what is the value of the position vector, for instance, at that time. So let's generalize the difference quotient, two vectors. Instead of asking how f changes with respect to x, we'd like to know how position changes with respect to time. And you can already sense, hopefully, that what we're talking about is velocity, because look at the units. Position is in meters, time is in seconds, meters per second. Those are the units of velocity. So we're taking the time derivative of the position vector. How do you take the derivative of a vector? It's the exact same procedure that you use for a single valued function of a single variable. You pick a particular time, which I'm calling t. You evaluate the position at that time. Then you evaluate the position at a slightly later time and take the difference. So the numerator here is the change in position. You could call it final position minus initial position over that small change in time. In the denominator is change in time. So it's really change in position over change in time. That's what a derivative is. It's the change in the value of a function compared to the change in the quantity on which it depends, or the independent variable, if you'd like to call it that. And then, of course, since it's a derivative, it's an instantaneous rate of change, you have to evaluate the ratio of these two deltas in the limit as delta t goes to 0. So it's still a difference quotient. The only difference now is that the change in our function is a change in a vector quantity. We recognize that quantity, right? Final position minus initial position. We actually have a name for that. That's called displacement. If it was change in velocity, we don't have a special name for that. We actually have to say change in velocity, change in acceleration, etc. But we do have this word for a change in position. It's called a displacement. This is a slide from a previous slideshow. We know what displacement is. Final position minus initial position is the vector that goes from the tip of initial position to the tip of the final position. That's if you've drawn your position vectors tail to tail. Final minus initial. Now, in the previous lecture, in the previous video, I was calling these vectors R2 minus R1. It still meant final minus initial, but right now, because we're trying to use the same notation that's often used in calculus for the difference quotient, it's more consistent to express the position as R at t plus delta t and the initial position at R of t. So all I've done is translate delta R over here. And remember, what we're really looking at is not just delta R, it's delta R divided by delta t. It's the rate of change with respect to time. How does the position change per unit time? So what is really going on here? What are we doing to delta R when we divide by delta t? Well, we've already looked at what it means to scale a vector, to multiply by a scalar. When you multiply by a scalar, all you do is stretch or shrink the vector. You don't change its direction. Now, dividing by delta t, isn't that the same as multiplying by 1 over delta t? Like if delta t was 10 seconds, to divide by 10 is the same as multiplying by 1/10. So what we're really doing when we divide this change in position by a change in time is we're scaling the vector. Now, if your time interval is greater than 1 second, if you divide by a number greater than 1, then you're actually making the vector shorter, as I've indicated here. Again, like if your time interval was a full minute. If you divide in SI units by 60 seconds, then your average velocity vector here, I'm kind of jumping the gun here, but this is really average velocity. Your average velocity vector would then be 60 times as short as your displacement vector. However, very often what we're doing is dividing by a small time interval, especially if we're talking about the limiting case of instantaneous velocity. If you divide by a very small number, like a hundredth of a second, dividing by 100th is the same as multiplying by 100. So you would actually be scaling your displacement vector up. Okay, think of it that way. If you've got a small displacement over some small amount of time, once you divide by delta t, you've now stretched that vector out. And again, we're really talking about the average velocity vector here. So I just really want to emphasize that delta r over delta t, which is average velocity, that vector points in the same direction as the displacement vector. All you've done, in turning displacement into velocity, all you've really done is change the length of the displacement vector. Okay, so average velocity. This should look familiar because in the one-dimensional case, which was covered in chapter 2 of our book, average velocity along the x-axis, say, was change in position, delta x over delta t. Velocity along the y-axis would be delta y over delta t. Well, now we're moving in the plane, so our change in position is called delta r. Okay, so we've got a coordinate system with an origin, and it looks like this graphic is specifying that at time 1, let's go with the ant example. At time 1, the ant was here. At some later time, which they're calling t2, the ant had made its way along this trajectory to position 2. See how this vector specifies where the ant is at time 2? And the change in position, r2 minus r1, would point from the tip of r1 to the tip of r2. So this is the displacement. Totally intuitive, right? To go from here to there, you could just execute this motion. And of course, that's not really what the ant did. But if you just want to look at the overall, like the net effect of your motion, it's just final minus initial position. And you can see that they're actually indicating here that this displacement vector has components. The dotted lines here. This is the displacement along the x direction, so it's natural to call it delta x. This is the displacement along in the y direction. Those two displacements together make this net displacement delta r. And just like I pointed out in the previous slide, they're showing you that the average velocity, that's this quantity right here, is parallel to the displacement. See that? Delta r, which is displacement, is in the same direction as average velocity. Because how do you get this green vector from the blue displacement vector? All you do is divide by delta t, or multiply by 1 over delta t. So you've just stretched or shrunk your displacement vector. They're still parallel. Now, in the one-dimensional case, we looked at how instantaneous velocity is defined as the limit of average velocity as your time interval goes to 0. And we can use the same limiting process here. Something I should point out, most of the graphs we've looked at so far are graphs of x-coordinate versus time or y-coordinate versus time. This is very different. This is y versus x. Neither of these axes is time. So what we're actually looking at is a picture of the path taken by the ant, which is often called the trajectory. So if you were, hovering over the ant looking down and watching it, this is actually the path that you would see it trace out. So in that sense, this picture is less abstract than those position versus time graphs. Those took some practice to get used to interpreting. This doesn't require really any abstract thinking. It's an actual picture of the trajectory. Now, if you compute the final position at times that are closer and closer to your initial position, it's a little misleading with the multiple 2's here. Just to pick numbers, maybe the position at time 1 was 10 seconds. Or excuse me, the time when the ant was here is 10 seconds, and maybe the time when the ant was here was 11 seconds. And then they changed it to 10.5 seconds, and then 10.25 seconds. So they're making delta t go to 0. It might be clearer if they had used a different number here, but they're evaluating the displacement vector for smaller and smaller time intervals. And do you notice how the delta r's are getting shorter and shorter? Of course they are, because the less time you have to move, the shorter the distance you're going to cover. So of course, the length of your displacement over a 1 second interval can be greater than the length of your displacement over a half second interval, and certainly like 1/100th of a second. So delta r is shrinking down to 0 as we take delta t down to 0. You can't go very far in a shorter and shorter amount of time. So the shorter the time interval, of course, the shorter the distance that you're going to cover. But the other interesting thing, and maybe the more important thing to notice about these displacement vectors, is they are approaching a limiting direction. It's not like this second one points in a wildly different direction from the first one. They're all starting to bunch up, and if you had made a picture like this with 10 vectors showing the limiting process here with the displacements, it would be really clear that your delta r vector is approaching a direction that is tangent to the curve at the initial position. That's it. So the limit of the displacement vector as your time interval goes to 0, that limit is a vector tangent to the curve at the initial position. Now, what's happening though to the displacement vector? It's getting shorter and shorter. So how did it suddenly spring back up to this length? What happened there? If delta r is getting shorter and shorter as it becomes tangent, why did it suddenly become a finite length again? That is because as you're executing that limit or approaching that limit, you're continuing to divide by delta t. So delta r gets smaller as delta t gets smaller, but that doesn't mean that the ratio of the two is necessarily getting smaller. Just a reminder here about the definition of velocity. It's really the limit of the average velocity as delta t goes to 0. Okay, and here's another point about the distinction between the graph we're looking at now and the position versus time graphs that we looked at previously, because this is something that actually confused me a bit when I first started studying this subject. In a graph of x versus t, we talked at length about the fact that the slope of the tangent line at any point gives you the instantaneous rate of change, or really the velocity. You can see the velocity on a position versus time curve just by taking the slope of the tangent line. And that's really not what's going on here. If you try to infer something by the or from the slope of this velocity vector, you're going to hit a dead end. The slope of this green vector tells you nothing about how fast you're going. It really just tells you the direction, because now we're talking about velocity as a vector. So there is a significance to the direction of this vector, but it's not how fast you're going. It's literally the direction that the particle is moving in the xy plane. If you'd like to know, or if you'd like to determine from this graph what the actual speed is, you would have to calculate the length of this vector. And that can be difficult to represent on the graph, because what if, after dividing by delta t, you find that the speed is a really large number? You can't actually draw an appropriately scaled vector because it might not even fit on your graph. As opposed to over here, where it's not that difficult to draw a tangent line no matter the slope, right? You can even draw a tangent line that has a slope approaching infinity. That's something you can actually draw on the paper. But this is kind of symbolic, if anything. Okay, so please don't get confused by that. The slope of the tangent line here on a graph of y versus x does not tell you what the speed is. It does not tell you the velocity. The velocity in this case is not just a number. See, over here the velocity is just a number. It can be positive or negative. Here the velocity is a vector quantity. In this class we need an arrow to represent it. And if you'd like to know something about the speed, then you would look at the length of the velocity vector. Okay, so this graphic summarizes that point. Please don't confuse the two. And again, your book they don't like to commit to x versus t or y versus t. They pick this generic s-axis. I just call it x. All right, I feel like I'm repeating myself here. What's the significance of this slide? Right. Once again, as you take this limit, yes, the time interval shrinks to 0, and that means that the length of delta r also goes to 0, because you can't move very far in a small unit of time. But the important thing here, and this is this idea from calculus that you really want to understand, just because these two quantities are both going to 0 does not mean that their ratio is 0. What exactly is 0 divided by 0? That's undefined, right? Well, if you approach it from one side or the other, if you zero in, so to speak, on that ratio, you can often find that it approaches a limit. It's some actual value. In this case, it's a vector value. But again, just because the numerator goes to 0 and the denominator goes to 0 does not mean that the ratio of the two is 0. Usually, well, I shouldn't say usually, but in this class, almost everything we look at, that ratio approaches some definite quantity. That's the quantity that we call the derivative. In this case, the derivative of position with respect to time. Now, we've already talked about resolving a vector into its components by drawing a right triangle, using trigonometry. Same thing here. We've already talked about the fact that any vector can be written in terms of its x component and its y component. You can use Pythagorean theorem to get the magnitude of the vector, right? You just square the components, add them up, take the square root. That's really converting from rectangular components to polar coordinates, or polar components. Okay. The last thing I'd like to point out, and this is not shown formally in your book, it's kind of just taken for granted, but it's nice to see the reason for this. Let's suppose that the position of your particle, whether it's a helicopter or a rocket, an ant, whatever, it depends on time. It's some specified function of time. That means the x-coordinate has particular time dependence, and so does the y-coordinate. And we've seen already how any vector can be written as a linear combination of our two basis vectors. You go this far in the I hat direction, and you go this far in the j hat direction. Let's use this expression for r to examine the difference quotient, or the limit of the difference quotient. We know that velocity is the instantaneous rate of change of position. It's dr dt. That's the limit as delta t goes to 0 of the average velocity, so final position minus initial position. And here's where we're going to take this expression for r and plug it in here. So since the position at any time is x-coordinate times I hat plus y-coordinate times j hat, here is that expression for r evaluated at time t plus delta t, right? You go x units in the I hat plus y units in the j hat, but I'm evaluating x and y at the later time. Oops, that's supposed to say, what is this, t delta? Let me fix that. Okay, I fixed it in this slide. In the next slides, this expression is going to be all janky again, so just ignore it. So position evaluated at the later time minus the position vector evaluated at the original time t divided by delta t. Now what can we do in the next step? We've got an I hat here and an I hat here. Just like in algebra back in high school. Let's collect like terms. Everything that's some number times I hat, let's put that together. And everything that's some number times j hat, let's put that together. And I get this. This is the x-coordinate at the later time minus the x-coordinate at the previous time. Take that quantity times the unit vector I hat. Do the same thing for the y-coordinate. Again, I'm sorry, this is supposed to say t plus delta t. Okay, that's better. Position at the final time minus position at the initial time. Same thing for the y-coordinate. And then, remember in calculus how you can say things like the limit of a sum is the sum of the limits. Let's do the same thing here. Let's evaluate this limit and then evaluate this limit and subtract instead of just taking the limit of the whole thing all at once. Remember how division is distributive? We have to divide this delta t into this quantity and this quantity. After I've done that, I get this. And like I said, I didn't go back and fix all the typos up here, so don't look at that. Let's focus on the latest equation here. So this is the limit of one quantity involving only x and delta, or I hat. Here's the limit of another quantity involving only the y-coordinate and j hat. Well, let's look carefully at this quantity. What is the limit as delta t goes to 0 of change in x over change in time? We've already looked at that. That is the definition of dx dt. That's the time derivative of the x-coordinate. And same thing over here. This is change in y over change in t in the limit as delta t goes to 0. That's the instantaneous rate of change of y-coordinate. In other words, we're looking at the velocity along the x-axis and the velocity along the y-axis. We have expressions for that, dx dt plus dy dt. And that's the result that we were aiming for. And it's very intuitive. It would have been your first guess if you actually knew what the position was as a function of time. Like if you were told this was t squared and negative 3t, how do you find the velocity? Your first guess would probably be, well, why don't we just take the derivative of each component? And that is, in fact, the correct way to do it if your basis vectors are these constant I and j hat vectors. There are other basis vectors you can use that are not constant. For instance, if you want to use polar coordinates, we may look at that briefly later in the semester, but almost always we will be using I and j. And if that's the case, the derivative of your vector is merely the derivative of the components. That's it. So if you happen to know how the x and y coordinates depend on time, you can just differentiate those two component functions, and that will give you your velocity vector. As for notation, you could call this dx dt, you could also call it v sub x. And it's understood, since there's no over bar here, there's no subscript ave, this is the instantaneous velocity in the x direction. This is the instantaneous velocity in the y direction. If you're wondering, what exactly does that mean, velocity in the x direction? Like, what if you're not actually moving parallel to the x-axis? Like the previous picture was moving, the particle was moving diagonally. So what really is the velocity along the x-axis? Well, it's this right here. It's the time derivative of x coordinate. That is the definition. So the next presentation will be some more worked problems, this time from chapter 3.